So, good afternoon, everyone. So I just wanted to check the list. Most of the lectures are taken. Shear will start, right, with maximum likelihood estimation.
Yes, she was here.
She was here, now she disappeared, okay. Good, but this will be only after Pesach. So we have actually everything until renormalization theory, which is, to my opinion, very interesting and helpful. But if somebody doesn't, I mean, if you don't fill it up and I just said it before, and you see a paper project that you really would like to give a lecture about, then we can do this, okay? So I'm flexible. Or also, if you think some of your research is very much related to the course, then you can suggest your own project and I will tell you yes or no.
And can we suggest our own lecture?
Yes.
As well?
If it is, I try to choose something that is helpful for everybody for later writing the paper project. So that was the purpose of selecting these lectures, but you can come up with your own idea. Okay? Good.
All the tirgulim will be uploaded to the...
Yes, yes.
Okay.
Otherwise there's no point, right? You should be able to copy-paste into for your paper project, okay? Good.
אפשר שכמה יעשו אחד מהם?
מה?
כמה סטודנטים ביחד יעבדו?
Two, not more. I don't want to have people working on this. Then three are not doing anything. Two is maximum. Good. Then today's lecture is about fractals. Right. And I read a very interesting article on the conversation that I put you there the link that you can read at home when you have some free time, and it's titled Mandelbrot's fractals are not only approaches, they taught mathematicians, also us, how to model the real world. And this article basically captures all the philosophy of today's lecture. It's really a nice popular science summary, to my opinion. So, and it deals to a large extent with he called himself the father of fractals, and this was Mandelbrot. Okay, he got quite good old age, and very interesting personality. Also, Shlomo Havlin met him a couple of times. Also, very difficult personality, but made big impact. And actually, he coined the term fractal. Okay, before mathematicians worked on fractals without calling them fractals. We will talk about it today a little bit. And Mandelbrot was actually the first one that realized that in order to describe nature, we need a new kind of geometry. Okay, that he then called fractal geometry, as opposed to Euclidean geometry that we learn in school, right? And this fractal geometry he first introduced and developed in his books Fractals from Form, Chance and Dimension and the Fractal Geometry of Nature. And there he wrote the very famous couple of sentences that in fact fractals are the rule in the universe. Shapes which are not fractal are the exception. Euclidean geometry is fine, we said, I love it, but it's quite clear that it does not give a reasonable presentation of the world. Mountains are not cones, clouds are not spheres, trees are not cylinders. Sometimes he says trees are not triangles. Neither does lightning travel on a straight line. Almost everything around us is non-Euclidean. Yes. What is fractal? What is fractal? That's the lecture.
Okay.
Okay. Right? So, and very famous, I think one of the most famous fractals is the Mandelbrot, right? Probably you have seen this already. It's also called the Apple Man. So it's something that you can dive into it until infinity and you will all the time get the same picture. So Mandelbrot was the first who made this step and said, okay, Euclidean geometry, when we have simple straight lines, triangles, circles, spheres, we cannot describe complex structures in nature. And simply, and it's amazing that nobody thought about this before, right? Because when you look at the tree, you see it's not Euclidean. It's not a triangle. It's not a cylinder. A mountain is not a cone, and the sphere is not, and the cloud is not a sphere. But mathematicians kind of avoided looking at nature, so to say. I mean, we will talk about this later today. Also, all kinds of objects that they could not kind of describe with their geometry, they called monsters. Okay, mathematical monsters, until up to the 20th century. And but another important contribution of fractal geometry is something that's called self-similarity. So we will talk about scale invariance in a moment, and self-similarity is very much related to it. So when you think about it, in physics we have usually translational symmetry. Okay, when you look into in solid states physics, crystals, you have always fixed length scales, right? Or you look at the ideal gas, then you have a mean free path length, right? So these are all these areas in physics. They have a characteristic length scale. They work on this assumption that there is a characteristic length scale with which you can describe the physics of a material or a gas or whatever, right? But when you go to complex systems or most natural objects, then you don't have a characteristic length scale and translational symmetry. You have a new kind of symmetry that is called scale invariance or self-similarity. So you cannot define a fixed length scale in a fractal, right? If I give you a fractal, a picture of a fractal, you cannot tell me at which length scale this was, the photo was taken, right? In contrast, when I give you a crystal, you can tell me at which scale a picture was taken. So, low characteristic length scale, fractals are scale invariant. Examples are, let's take the tree example. You see, when you lay under the tree and you look up, you see branches of all length scales. You see branches that are almost at the magnitude of the tree itself, and you see small little branches that are of the size of leaves. So a couple of examples, because some of you may ask yourself what are fractals exactly. So let's look at some examples. So here is a computer fern. Somebody's making popcorn. So you see that if you zoom into this little leaf here, you recover the original object, right? And then you can zoom into this one, and here you have another. So it's you don't have a fixed you don't have a characteristic length scale. You never know where you are basically, right? Of course, everybody when he looks at the broccoli, this Romanesco broccoli, you see this is the whole broccoli. But if I give you this picture, you won't be able to tell me that this is the length scale here is centimeter or millimeter. Okay, so these are two examples of fractals, and perhaps you also remember in our class 2 years ago. Also, right, we did differential equations together. We had here the logistic map, which was an example of what? Bernoulli. Okay, it was a Bernoulli equation that we took it as an example to model disease spreading in the population, in the general population. And I told you we will talk about this in 2 years in computational physics again. And it turns out that this logistic map that you see here, we will have a lecture about this. I think, Josef, you are going to talk about it, right? About logistic map. Logistic map, yeah. So we will hear more details about why this is also an example of a chaotic system and stuff like this, and why it is important and where it appears in nature. But here I wanted to actually show some short movie clip about the fractality of the logistic map.
Paradoxically.
Now you see it, right? It is some stupid commercial. Can I skip the commercial now? Okay.
The more we save, the less we have.
Yes.
It's paradoxically not
Good. Here, you see a logistic map, and if you zoom in, it's a fractal, right? When I stop here, you don't know where you are, basically. There's no fixed characteristic length scale. We can continue with this until everybody of you is falling asleep. It also works to look at fractals to relax yourself. It's shown really scientifically that you can relax yourself by looking at fractals. Good. So that's an example. This was an example from chaos theory. Here another example from so these are the Lichtenberg figures, so-called Lichtenberg figures. These are discharged patterns. Okay, so you can here you have a lightning. Okay, lightning is a Lichtenberg figure. So Lichtenberg, Georg Friedrich Lichtenberg, Christoph Lichtenberg, he described this phenomenon already in the 18th century. He was a German. He said, "Ein Teil sieht aus wie das Ganze. A part looks like the whole." Right? And you can simulate these Lichtenberg figures in the lab as discharge patterns in acrylic glass, for example. So here is a example that I need to has an idea how to do this better, to switch between PowerPoint and you all the time have to close the PowerPoint and show it. It's a little bit strange. Okay, so here is the movie. So what you see here is a acrylic glass that is charged with 2.5 million volt, right? And now somebody takes here a hammer and a nail, and he is discharging the glass. And let's see what is going to happen. You get a Lichtenberg figure. Okay, so you have kind of impurities in the acrylic glass where so discharging happens according to a fractal, basically. And another cool thing is so I don't know, someone of you knows watches the Good Doctor, some series, The Good Doctor.
Ah, perfect.
Yes, you know it. Sean Murphy is an autistic surgeon.
Yes,
He's
yes.
American. And you remember in the last series there was one guy that was he worked on some roof and he was struck by lightning, right? I don't know if you remember. And then he had some rash on the skin, and then Dr. Lind came in the room and said, "These are Lichtenberg figures." And my wife and my daughter, they are watching. I don't watch this regularly, but I could explain them what is a Lichtenberg figure. Yeah? So it looks like this. I want to show you.
This is a...
Yes, okay, we can always ask questions.
Can you explain when we have to work in fractal geometry? Because usually curves are not a sphere, but we approximate it to a sphere. We can solve it.
Yes.
But it's not really a sphere. So when is the approximation is not good?
When you are far off. So if you are working on something that it always depends how far off you are from the dimension 3. Okay, when you have a fractal object that has a fractal dimension of 2.6, then to approximate it as a sphere is not a good approximation. But it always depends what you want to achieve.
There is no some specific kind of systems, not like
there's no rule of thumb.
No.
So you have to always consider it on the case.
Okay.
Yeah. So yes. So look, this is. Can you see it, Ashley? Yeah. Ashley, you cannot. Maybe in the front rows you can see. This is a Lichtenberg figure on the skin of someone who was struck by lightning. Okay. So this happens because the little capillaries in the skin, they are basically not really burnt, but almost burnt. I mean, they are destroyed basically by the large voltage, right? And then you develop these Lichtenberg figures, and they usually disappear after a couple of days or weeks if you survived lightning. So yeah, and she says it's important to recognize this because when you see somebody unconscious, you know what happened to him or her.
This is a skin injury caused by a lightning strike. But get this, it's not actually a burn. They're called Lichtenberg figures, and they show up within an hour of a lightning strike, and then they just disappear within a few days. So it's a clue that can be really important if you're seeing a patient who's unconscious or who doesn't remember being struck by lightning.
This is a doctor on TikTok. She's all the time. But this I find interesting. But don't try it at home, okay? So this is not something recommended only that you do some physics experiments and get addition to physics. Yeah. Okay, another example, fractals in chemistry, when you have copper deposition from a solution of copper sulfate, you get this nice shape, and you zoom in and you recover the same shape again. You have a mangan oxide layer in limestone, and a big question is now, why did nature choose fractals at all, right? I mean, why not Euclidean geometry? Everything is very easy. And we don't know exactly why, okay? It's still heavily researched question, but one kind of convincing argument is that perhaps a system that has many lengths or time scales is more resilient to external perturbations. If you think about the tree and the many branches, the branches of many different length scales, it's more resilient towards a storm. So it's much more difficult to put a object with many length scales into resonance, right? So the storm is not flowing constantly, it's flowing periodically, right, if you think about it. And it is easier to put an object with only one length scale into resonance, right? And by distributing, you have a distribution of length scales, you can't basically put the tree so easily into resonance. And a big field I work on is, and this also contributing to this argument of resilience, is that in physiology and medicine, we have a lot of fractal structures in organs. So if you look at kidneys, so this is here all the blood vessels in the kidney, then it forms like a tree, right? You have a tree-like shape in the kidney or in lung tissue. And the interesting thing now is that you don't just have fractals in the structure of these organs, in the kidney and the tissue, and also the blood vessels of the heart follow a fractal shape, but also the time series, so the signals that you record from these organs, they also show fractal properties, and we will talk about this later in the semester when we learn about time series analysis. And so basically we have the symbiosis. We have fractal structures and fractal time series. So blood diffusion in this organ shows fractality. So that improves probably the perfusion in this organ, or respiration and the heart rate signal, they show fractal properties. And when in the 90s there was a famous study published in Nature of a group in Boston that went to the intensive care units and suggested to the medical doctors to modulate their respirators. You know, when people come after accidents and they have brain trauma, they are in coma and they cannot breathe by themselves, they get intubated, right? They get the breathing basically from the outside, and over until up the 90s, this breathing rate was constant. It was always given with the same, it's a sine wave basically that they gave to them. And these researchers from Boston University, they suggested, based on analysis they did on animal models, that perhaps it is better to modulate the breathing in a fractal shape, similar to what our breathing actually, our breathing signal is not monotonously always a sine, but it changes in a fractal way, right? And if you give the same modulation to this breathing machine, then you improve much more the oxygenation in the tissue, and people it increased survival probability of the patients. So this is an indication that fractal structures and fractality in the timing is something that helps to increase resilience. Good. And wanted to talk a little bit more about this the lung as a fractal. So it's very interesting when you take a lung. You know, it has we have two wings of the lung, or two parts of the lung, right? And when they split, so you have a main split, and then you have each branch splitting to smaller and smaller branches, right? And this happens, interestingly, according to a Fibonacci series. If you remember Fibonacci, this was when you create a Fibonacci series, you always add the two predecessor numbers to obtain the next element, right? So 2 plus 1 is 3, 2 plus 3 is 5, and so on and so on. And when people did anatomical studies, they noticed the same going on in the lung, right? You have here the main branch, and then they split into 2, and then these 2 split into 3, into 5, into 8, and this happens until up to 10 generations, which is, I mean, amazing, right? And the two researchers that published this paper, in, I think it was also in Nature, they called it the fractal Fibonacci lung tree, and argued quite convincingly that this improves the physiological efficiency. And actually this paper was the basic for this other Boston group that came to the intensive care unit and suggested to put a fractal modulated time series into these respirator machines. Good, very short history of fractals. We have talked about some of this stuff already, but mathematicians worked on fractals for several hundred years already. There is some work of Leibniz in the 17th century that is based on self-similar shapes, and but he was considered by his peers at the time a little bit crazy that he worked on stuff like this, where there's no real geometry. And as I told you, they called it basically for 200 years mathematical monsters, because they couldn't understand and describe this kind of objects. And it took until up to the 19th century, when another famous mathematician, Karl Weierstrass, he presented a function. He gave a talk at the Prussian Academy, and he presented a function which could be considered as the first mathematical fractal. And the function is simply this one. This is the function. How would we call it today, this function? What does it look like? It's a Fourier series. Okay, Fourier series. And you have here these these two constants, not constants, variables actually, a and b. And by changing a and b in a particular way, you can reconstruct the fractal. So here is an example I took from Wikipedia, where b is changed between, is modulated between 0.1 and 0.5. So this is 0.1, and now it goes into the direction of 0.5. And then you see that you kind of recover a fractal shape, right? So if you would zoom into this side or this side, you would see something that really is self-similar to the whole object.
Fractal is always some kind of function which is smooth. It's continuous but not smooth, or it's only this case?
Yes, it's never smooth. Okay, you have to have something that is. I mean, there are not many. Actually, Mandelbrot tried several times to give definitions, and every time people criticized him on the definition. So in the end, he said, let's give up on the definition, you know. But it is basically understood as some geometrical structure that is rough, okay. And when you zoom in, you recover a picture that is similar to the whole picture. Basically, this is the self-similarity and scale invariance. These are the two things. I mean, there are people that said, okay, let's call everything that is doesn't have a integer dimension, a fractal. But then Giano, we will talk about him in a minute, came with his fractal that had exactly a dimension of 2. It was a fractal, but it has an integer dimension. So then they had to reconsider again until they gave up and they said, okay, just self-similarity and scale invariance. Good. Then after Weierstrass, it took again a couple of years, and finally in the 20th century we had people like Georg Cantor, Felix Klein, Poincaré, Helmut von Koch, Gaston Julia. Gaston Julia, actually, he did the work on which Mandelbrot later based his work and came up with the Mandelbrot set. So
the Julia set, right?
It's the Julia set, right. It's the Julia set. And then we had Václav Sierpinski. We will talk about his fractal also in a minute. And so they presented their own fractals, and finally in 1975 the name fractal was given by Mandelbrot. Before they were just calling it self-similar shapes, self-similar structures. And but the real push to fractals was given with the availability of computers, of course, in the last 40 years, because now you could do simulations. Before it was very difficult to describe fractals, and now you could simulate them. And in fact, fractal geometry is much more suitable for computers than Euclidean geometry, because in the computer you also have this recursive language, right? The recursive language you use also in order to reconstruct fractals, and when somebody will present to us the way to generate fractals, how to program it, how to generate it in the Jupyter notebook, then you will see that it's a recursive way of constructing things. So let's dive a little bit more into it, and the two types of fractals that we need to distinguish are deterministic and random. Deterministic fractals, also mathematical fractals, they are ideal. Okay, they are mathematical, correct. You can zoom in until you just don't have power anymore, but it is always recovering the same picture, right? The self-similarity is so every small part of the picture, when magnified properly, looks as the whole picture. This is a property of the fractal and not a definition. Okay? And here are two examples that you probably are all familiar with. One is the Koch curve, or when you put it in, when you continue this when you start from a circle and you or not a circle, but you a square, and you kind of construct this, then you have something that's called the Koch snowflake, right? And here you have the Sierpinski gasket. And I just wanted to, I mean, how would we construct it? The Koch curve, it's very easy. We take one line, we divide it in 3 equal parts, and the middle part we replace by this chubchik. Okay, this, I don't know how to call it better.
A kind of triangle.
It's not, yeah, okay, it's 2/3 of the triangle. Okay, 2/3 of the triangle, and then you repeat it. In the next iteration, again, you take this part, you cut it into 3 parts, and you replace the middle again by 2/3 of a triangle, and so on and so on and so on, until you get this nice kind of snowflake shape. And now I want to ask you, what is the length of this Koch curve?
Infinite? Infinite?
No, it's not infinite. You see that it's not infinite.
Somewhere between 1 and 2.
Okay.
Okay, somewhere between 1 and 2. I would say, David, you should have heard this already. So what is the length?
Depend on your ruler.
Yeah, exactly.
I
Thank
don't
you.
want to spoil it.
Thank you, Leo. No, you can spoil it. So it depends on the length of the ruler, okay? So if you take a big ruler, okay, let's say your ruler is this length, okay? I have here, this is my ruler. Then the length of the Koch curve is 1, right? Now I cut this into 3 pieces of equal size. So I have a ruler size of 1/3. And now I can go into more detail, right, of the curve. And I will have now 1, 2, 3, 4 parts. So it will be 4/3, okay? And then I can take my 1/3 of the ruler and I can cut it again. I have 1/9 of the original ruler, and I will recover, if you count it, 16, right? So 1, 2, 3, 4, and so on. So I will get 16. So we see that the length basically increases, okay, according to 4/3 to the power n, when n is the duration, yes.
So if I do it infinity times, I have infinity.
Okay,
length.
good. Yes.
Because not
Wow.
rebel.
So in this case, yeah, you're right. So it's infinite length. Yeah. If you go to a scale that is smaller than the proton, it gets a bit difficult. But in general, you can say it's infinite. Yes. And at the same time, when my length increases in this way, right, 4/3 to the power n, my ruler length needs to decrease, right, by 1/3 to the power n. So that's so I have here a relationship between the two, right? So it's the dependence between L and the ruler length, and this dependence is given by what? If you think about it.
Power.
It's
a power.
It's a power law, yes, and it's the dimension, right? If you think about if this object would look completely different, then the relationship here would be also different, right? So, so the relationship between the length and the length of the ruler is given by the dimension. So we have to talk a little bit how we actually calculate dimension. And let's go to the simplest thing we can come up with, and these are Euclidean shapes, okay, like lines and squares and cubes. And again, delta is my ruler size. R, which is the inverse of delta, is the scale I'm working on, or magnification. I'm talking about both because some books use delta, the ruler size, and some books use the scale R. But you should know that they are just, the one is just the inverse of the other. And n is now the number of line segments or squares or boxes to cover the object. Okay? So if I go here from a ruler that is has a length of 1 to a ruler that has a length of 1/2, right? I would need 2 line segments to cover this object, right? And when I take a square, when I here take half of the length of the square, I need 4 squares to cover the big square, and here for the cube, obviously I need 8 of these little cubes to cover the original object, and you already see where I'm going to. That the number of little line segments and boxes that I need to cover linear or one-dimensional shape or two-dimensional, three-dimensional shape. So this scales with R, so the scale to the dimension, right? Or if I take the ruler, then it's 1 over delta is equal to 1 delta. Actually, it's no, here it's exact. It's 1 over delta to the power of d, and as all said correctly, d now I recover by just taking the log, right? I take log n divided by log r, or minus log n divided by minus log delta, and then I recover the dimension. It's kind of trivial for these Euclidean shapes, but it's very helpful now to use this approach when we are going to calculate the dimension of the Koch curve. And someone can tell me how to do it? So remember, it was log n divided by log delta. So what is, first we have to decide on the ruler length. Choose 1/3, right? So ruler length is 1/3, so it would be log 1/3. And how many line segments would I need in order to cover the object? 4, right? So it's log 4 divided by log 1/3. And if you just calculate this, you get a fractal dimension of 1.26, fractal dimension of the Koch curve, which is compared to Euclidean shapes. We can say the Koch curve is more than a line, but less than an area, right? Area would have d equal to 2, and a line would have only dimension of 1. So it is just, it's more a line than an area. Since this, so, and we call here df the fractal dimension, and since this worked so well, we can do it also for the Sierpinski gasket. What would be the fractal dimension of the Sierpinski gasket? Sure, any?
I don't remember. I need to take the ruler size. Don't remember how we did it there.
Ah, okay. Sure, any idea? But let's do it together. So we go from here to here, right? What would be my R? It's 1/2, right? I know R is 2. So the ruler would be 1/2. So R is 2, right? Because I have here the whole one. Now I have half the ruler size. So R is equal to 2 because I go in by a factor of 2. And how many of the triangles I have? 4. No, 3. I take out the one in the middle, right? So it would be 3 log 3 divided by log 2, right? So this is what we get. So it's scale. You can also take a minus and then log delta, which would be 1/2, but you have the minus, so it comes out the same. So log 3 divided by log 2, it's 1.58. It's a little bit, it's exactly between being a line and an area, right? So, and you can see this here, it gets very airy, okay, this object, yes.
What is n and what is r?
N is the number of boxes we set in order to cover the object. Here. You see, it's the number of line segments or squares or boxes to cover the object. So if you have a line, then it would be 2 line segments. If you have an area, then it would be squares, or it would be boxes or little cubes in order to cover this cube object. So usually, as I said, the fractal dimension is not an integer number. So fractal curves, as we saw before, they have a fractal dimension that's usually between 1 and 2, more than a line, but less than two-dimensional shape. Exception is what I said before, this piano curves from the Italian mathematician that just suggested the following fractal. You take three sides of a square, and then you replace the first side here, you replace again by three sides of a square. They came up with crazy ideas, you know. And then you take the middle and replace it by these three sides of a square, and then you take the end, you know. And you do this consistently over and over again, and in the end you get, this is your fractal. I mean, the whole thing is a fractal, but this is after 10, 20 iterations, and if you calculate here the fractal dimension, you will get 2, exactly 2, right? So this is an example of a fractal that has really an integer dimension and is close to an area. But you can also have less than 1 when you look at the Cantor set from Georg Cantor, that not Ido Cantor, but Georg Cantor, that they are also not related because this one is written with C. Or maybe they are, I don't know, I have to ask him. So you take one line and you cut out the middle, okay? And you do this in every step, cut always out the middle, and you end up with something like this. That is also, it's also called Cantor dust, you know, and it's lower than one-dimensional object. It's a little bit difficult to imagine, but it has a fractal dimension of, I think, 0.78 or 0.8. You have to look it up. Good. So these were the mathematical fractals, the exact deterministic fractals. Any questions about this?
And
No.
does the Plano curve get to 2 because it's not always in the middle?
No, because it just fills the whole two-dimensional space.
Would it if the squares were in the middle?
If you
3
would
times?
do it differently, I think, so you suggest instead of taking the middle, you take always the side or something?
You take
Okay.
always the middle.
Always the middle? I think, I cannot imagine that nobody has tried this because it's an obvious thing to do. I think you run into problems then to draw it, you know, maybe that's the reason. But I don't know. But I think you will also end up with maybe after a couple of iterations you don't have space anymore to draw it. I don't know. I don't have the answer. Yeah, homework for you. Draw it until iteration 20 or so. I don't know. Good question. So that's about deterministic fractals. Now let's go to random fractals. Okay? And one of the most famous random fractal is coastline. Okay? Everybody sees what is this? What coastline?
Britain.
It's Britain, it's even written there. Right? England, Wales, Scotland. What is this coastline? Leo?
I don't remember.
Okay. I give you a tip.
Norway.
Norway. Here's Oslo. Okay, also interesting coastline because you have the many fjords there. Right? And so the question was now, in a famous paper by Mandelbrot in Science in '67, how long is the coast of Britain? This was the title of the paper. What would be your answer?
Depends on the rule.
Depends on the ruler.
It depends on the ruler, exactly. So the whole paper, which is now cited 10,000 times, just deals about that it depends on the ruler, you know. But the thinking in the 60s was not like we are thinking today after this lecture. So basically, what you are doing is you measure how your number of line segments to cover the coastline depends on the size of the line segment, right? So if you take here this coast, okay, I don't know if you can see it. So you have here some line segments with which you cover the coastline. So how does the length of the coastline depend on the resolution or the scale of observation or the ruler length? Which coastline is this?
It's like Italy.
Huh?
Italy.
Italy? No, but I give you a tip.
Monaco?
All the Americans should know this.
New York.
No Americans.
There are no Americans here?
Canada.
Ah, close.
Mexico.
No, far away.
Florida.
So this is Cape Cod. Okay, why Cape Cod is important for American history? Ben Gurion gave a very big speech. One of his biggest speeches in front of the UN was about how the Mayflower. So he said, ask American children about who was the captain of the, or what was the ship called that carried the first pilgrims to America, and probably, okay, some may know, but if you ask Israeli children, who was the leader who brought all Am Israel to Israel, to Eretz Israel, then they will know it's Moshe Rabbeinu, but nobody can tell you what is the name of the captain of the Mayflower, right? So this was his argument. So the Mayflower, they sailed from, actually from the Netherlands. They first went from England to Leiden, and then from there to over the Atlantic, and they first landed in what is nowadays Provincetown. It was in the winter, so it was half of the people died, I think, and later they continued to Plymouth, where they established the first settlement. So, yeah, so when you go to Provincetown, you have a lot of stories of settlers. Very interesting, very nice place to travel to, and yes, and this is the island of the rich, where Obama and the Clintons, everybody has a house there. I think it's Mary's vineyard, Martha's vineyard. No, yeah. Anyway, what I wanted to say is you basically map this problem of measuring the coastline onto what we just discussed with the Koch curve, right? So you want to study how the ruler size relates to the length that you measure. And now coming back to our question about the coastline of Britain, you take different sizes of the ruler. So here it's 100 kilometer, and you measure around the coastline, and you get one value, right? So here it's the ruler size basically in this direction decreases, okay? Ruler size decreases, and the length of the coastline increases, right? Because you can measure more and more details. If you have 50 kilometers ruler length, then you measure a longer coastline. And you do this for several ruler lengths, and what you obtain is this straight line on a log-log plot. And we have learned that the slope of this line is our fractal dimension. So the answer to the question, how long is the coastline of Britain, is that you answer with the fractal dimension. Okay, this is much more value than to give a number for the coastline itself. So doing this with the computer, or in general, is quite cumbersome. Why? Can somebody tell me why this is not a good way to calculate the fractal dimension? How would you do this? Imagine you had to do this as a homework. What's the problem here? It's very difficult to decide where to put your ruler because you have all these little fjords, you know. So are you going inside the fjord or are you going out? I mean, going around the fjord. So very tricky to do this. I gave this once to students as a project to do this with the computer and to present to the class, and they almost killed me because it's. I mean, by hand you can do it, but to program it is not very easy.
כמו שהיקף המעגל 8 פאי, משהו כזה. אותו רעיון.
8 פאי?
כן, אם אתה עושה את זה במדרגות, כמו מעגל מפוקסל כזה,
שפאי שווה ל4,
אתה יכול.
Okay.
So he's going the.
Okay.
It's like
Yes.
the box counting method.
Yes. Yes. Yeah.
That's the same. Yeah.
Yeah, it's similar. Yeah, but
Shall we double
this comes to what Leo said, that it's preferable to use something that's called the box counting. Okay, instead of taking a ruler and going around the coastline, you cover your image with boxes. Okay, with squares in this case, and you for particular size of your squares, you cover the image basically, and then you count in what box, I mean which box is covered by the coastline basically, right? And you get a certain number, and then you decrease your box size or your square size, and you do the same procedure, and you mark everything that is covers the coastline, and then obviously if you plot, so here in this case we called it before delta, okay, now it's called epsilon. So if you have bigger sizes of your boxes, then you have a smaller, I mean you have less, you count less, less boxes that cover the coastline, and the smaller your squares are, the more you count, okay? The more boxes you count, and then if you do here again, you do log plot, you fit the line through it, and you discover your fractal dimension according to the formula that we discussed before. And so practically it would look like this, okay? You mark all the boxes that are have any line of the coastline in themselves. And when you take smaller and smaller boxes, it's more and more of these boxes get filled. Good. So you can do this, and I think there's one project that has this as a paper project. So here would be the values that are obtained. You can repeat this for the paper project and write some algorithm that is doing it. And we have here 4 coastlines and the fractal dimensions of these coastlines. Can somebody tell me what is which? Australia, good.
Britain.
Which one? This is Britain.
Yes.
This is here the
Ireland.
This is
Ireland.
the enemies.
This is Sweden, if I remember.
Norway.
Norway.
Okay,
Norway.
Sweden is here.
Oh,
Sweden is next.
Sweden, Norway.
Norway. And these are the other enemies. Here. South Africa. And now look at the fractal dimensions. South Africa has 1.05 and Norway has 1.5. Why?
Because South Africa is more smooth.
It's more smooth, right? It's more smooth. And Norway has all these fjords, right? And because of this, when you go inside with smaller and smaller rulers, so to say, then you get a longer and longer coastline. So basically the fractal dimension here gives us a measure of roughness, okay, roughness of coastline. If you would do this for Israel, what would you get?
1.0 something. It's very smooth.
It's very
smooth. It's 1.01 or 1.02.
Maybe only around Haifa.
Exactly. What contributes a little bit to a non-integer number is Akko and Haifa. Otherwise, if you take out Akko and Haifa, you would get 1 because it's so smooth, right? And so we are actually quite close to South Africa regarding the coastline, but not in the thinking, basically, right? So yeah, so measure of roughness, and then you can also look at this broccoli that we talked about before, Romanesco broccoli, and we said we have here this nice scale invariance that at this resolution we don't know at which scale we are, but you can do an experiment at home, and around Pesach they sell this Romanesco broccoli. It's only around Pesach that I get this Romanesco broccoli, I don't know why. But it's very tasty and beautiful, and you can, a couple of years ago I did this with my daughter. You buy broccoli, right? It's a little bit more expensive than regular broccoli, but it's worth it. And then you eat 2 and you continue with 1. And what you're doing is you just split it apart and measure the typical size and how many pieces you have, okay? And you can do this, so you break it to smaller and smaller parts, and all the time measure the typical size of your parts. Then you just eat everything after you wrote down all the values, and then I got something like this. If you start with the biggest, so it has a 4 to 8 centimeter, and you have 2 pieces, and then you go smaller, you break them apart, you have 2 to 4 centimeter sizes, 9 pieces, and the very small ones, not so small, but 1 to 2 centimeter, we got 79, and then you just plot it. Here is the number of pieces over the size, and okay, so this is a fit through 3 points, okay, so you can play with it, but I mean, you get something that is not integer, okay, that's the point. So we got something around 2.66. If you say I got 2.56, it's also fine, or 2.7, it's something that is less than 3. And more than 2.5 is completely okay. And another thing you can do if you have too much time is to calculate the fractal dimension of bread. Okay, so this actually, there's some article in the journal, it's called The Physics Teacher, where they recommend to physics teachers how they can make their class more interesting. And one thing they suggest there is to study the fractal dimension of bread and compare white to kemach maleh, to full wheat bread experimentally, and they also took coconut cake, okay? So coconut cake, this is multi-grain bread, and this is white bread. So this is all made in Italy, so I believe this was tasty. Because if you buy coconut cake and multi-grain bread in the United States, it's not so tasty, I'm sorry. Even not from Trader Joe. And how you do it is you cut your baguette, for example, the white bread, you cut in little cubes of different size. Then you smash it a little bit, that you get spheres. Then you can easily measure the diameter of the spheres, and you plot here the diameter of the sphere on the y-axis, and on the x-axis you measure the mass of the object, right? How heavy are the spheres, and you do this to repeated measures, and then you we learned on the log-log plot that the line fit is a measure of the fractal dimension. So what would be your guess of the fractal dimension for wide breadth compared to multi-grain breadth?
Lower.
Hmm?
Lower.
What is lower?
The white bread.
Why?
Because the whole wheat has all these little parts, all these grains.
But let's get back to the experimental procedure. You're cutting it in cubes and then you smash it into. So what would happen for the white bread and what would happen for the Kemach Maleh?
White bread have a bigger
yeah, why do you think?
Because the mass of the Kemach Maleh is bigger.
Because it's denser, right? So you have less air bubbles inside. In the white bread, when you look into baguette, there's a lot of air bubbles, right? And if you take, the worst is the German bread pumpernickel. I don't know if you know this. It's very massive. You can kill somebody. So this is very massive dark bread. There's almost no air inside, and you get very solid sphere when you smash it. So this plays a role, the density. So according to this, when you have so if you have more air bubbles inside, right, then you get a higher fractal dimension. And when you have less, when it's more dense, you get a lower fractal dimension. Okay, and the coconut cake is the densest, so it gets lowest fractal dimension. So if you have some time, this you can do also before Pesach, because during Pesach it's not recommended. Yeah, okay. Any questions about this? Okay, so there are 2 lectures after Pesach on fractals and a couple of projects on fractals. If you have questions about this, you either ask next week or by email. Good, then we already finished.
Thank you.
See you. No?
מערכות קצת